Jai Hind and good morning. I am Professor Devendra Singh, and today we are going to discuss about the second part of this topic for elastic constant, their relationship. In the last lecture, we have established the relationship between elastic modulus of elasticity and the bulk modulus. Here, we will try to establish the relationship between modulus of elasticity and the shear modulus. Right. So, before going to the topic, ये डिलीट करना पड़ेगा.
यस सर, रिलीज कर लेंगे.
अच्छा, मुझे लगा वहां से ये आगे देखें. आगे तो नहीं है. ठीक.
तो आप इंट्रोडक्शन तो दे दिया था आपने.
वो रिकॉर्ड हो गया.
यस सर, आप वहां से कंटिन्यू.
जहाँ से हम कह रहे हैं, क्या कह रहे हैं कि बिफोर गोइंग इनटू डिटेल.
यस सर.
Okay. So before before going to establishing the relationship, we should discuss about the concept of normal stress on any oblique plane. For example, this is a block and it is subjected to biaxial state of stress sigma x, sigma y, along with a shear stress like this. This is tau xy, this is tau xy, and we need to determine the normal stress sigma n on this plane. Though if we do analyze the equilibrium of any portion of this, we will easily get the relationship for normal stress on this plane, due to this complex state of stress, that is sigma n is equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. This relationship we can easily obtain, and if I refer this relationship, and I consider this block is subjected to pure shear state, that is the normal stress subjected to the block is 0 and the magnitude of shear stress is tau xy. Then sigma n on any plane at angle theta will be equal to plus minus tau xy. I consider for the sake of simplicity tau xy is equals to tau. Plus minus. Why it is plus, then it will be considered a tensile stress. Why it is negative, we consider this is a compressive stress. So if you want to get some stresses on the along the diagonal, so I just release this, it is subjected to only pure shear. So this is the pure shear, and this is one diagonal A, B, C, and this is another diagonal. This angle is theta, that is equal to 45 degree. So for AC, this is 45 degree, and for For BD, it is 135 degree. Theta is equals to 135 degree. This is theta. This is theta. So if you put this value here, you will get what is sigma n. So after that, you can easily obtain this situation. It will elongate along this, along the AC, because you will get the positive for AC, and it will contract along BD. And in this state of stress, it will distort to some new form if it is permitted, though we will consider this is a rigid material. In fact, there is nothing which is perfectly rigid. We consider the materials are resistant, right? So we will move to the our topic with this concept. I consider a square block. This is a square block grounded, and it is subjected to a shear stress tau. I label the points, corners A, B, C, and D. Then AC is the diagonal. Under the effect, it may get distorted like this by an angle theta phi. Similarly here, it is phi. This is D prime, this is C prime. Now I join AC, BD, and B prime, D prime. And it is evident from this figure that AC prime is greater than AC and BD prime is lesser than BD. So BD is subjected to the compressive. BD is subjected to compressive stresses and AC is subjected to normal stresses, tensile in nature, that is tau in magnitude. This is tau in magnitude. Now from C, I drop a perpendicular on A C prime. This, I suppose this is M. So now I will try to find out the change in the diagonal AC. So change in the length of diagonal AC is C prime M, right? C prime M. So change in the length of diagonal AC is equals to C prime M. And what is C prime M? This is C prime M is AC prime minus AM. AC prime minus AM. This is C prime M, change in length. Original length is AC. So if I write epsilon, then this is C prime M upon AC. This is the basic definition. This is the basic definition. Now if I consider the effect of the stresses in the material. So net strength epsilon is equals to sigma along AC upon E within the elastic limit, sigma AC upon E minus sigma BD upon E. AC and BD are mutually perpendicular planes. So I consider AC is the longitudinal direction, then BD direction will be considered a transverse or lateral direction. And I have discussed that sigma BD is negative or compressive in nature. Compressive in nature. Now Poisson ratio will come into the picture. So in the lateral direction to BD, sigma BD will contribute this strain multiplied by Poisson ratio nu. This is the expression. So epsilon is equals to tau upon E minus nu times minus tau upon E. What you have obtained, tau upon E plus nu times tau upon E. So one expression I have obtained, epsilon is equals to tau upon E 1 plus nu. This is expression number 1. This is expression number 1. Now I consider this distortion. So tan phi, refer the triangle BCC prime. What is tan phi? Tan phi is equals to CC prime upon BC. Right? And since the material of this block is rigid, therefore the distortion or deformation is negligible. So this tan phi may be approached to phi. We can write phi is equals to C prime upon BC. Now refer this triangle here. Now refer this triangle. So what is C prime? So C prime is nothing but this is C prime M upon cos 45. C prime M upon cos 45 BC. Right, this is phi. Now what is BC? What is BC? So C prime M upon 1 by root 2, that is cos 45, multiplied by BC. BC is AC sin 45 degree. Considering this triangle. This is square, so this angle, both are 45 degree. So what we will get? We will get 2 times C prime M upon AC. Now this is equation number 1. This is equation number 2. Change the equation number. From equation number 1, what I have obtained here, phi is equals to 2 times epsilon, or epsilon is equals to phi by 2. This is equation number 3. Now if I consider the equation number 2 and 3, because from both the equation we have obtained the net strain in the direction of diagonal AC. So we can equate equation number 2 and 3. What we can obtain, we just equating equation number 2 and 3, and we will see what we can get. Right. So if we equate, we will get this is 5 by 2 from equation 3 is equals to tau upon E 1 plus nu. Now rearranging the term, what I will do, I will take E on the left hand side of this equation. E is equals to 2 times tau upon phi 1 plus nu within the elastic limit, more precisely within the proportionality limit. Tau is equals to G phi according to the Hooke's law. So tau upon phi is equals to G, that is modulus of rigidity. So now just put this value in this equation. What we will get? We will get the relationship. E is equals to 2G 1 plus nu. This is the desired expression or desired relationship between modulus of elasticity and the modulus of rigidity. So till now, what we have established, the relationship between the modulus of elasticity and the modulus of bulk or bulk modulus, modulus of elasticity and modulus of rigidity. Now we will try to establish the relationship between, we will try to establish the relationship between E, G and K. E, G and K. What is the relationship? So we have established a relationship between E and K like this. E is equals to 3 times K 1 minus 2 nu, and E is equals to 2G 1 plus nu. From these two equations, we need to find the relationship between E, G and K. So what is our basic requirement? We should try to eliminate this nu from these two equations. Nu is a property of material. The value for a particular material is a fixed value. So from both the equation, we will have the same value. So in the next lecture, we will establish the relationship between E, G and K. I hope in this lecture you have enjoyed and you have learned about the relationship established process of E and G. So tomorrow we will again start with the same problem. Thank you and bye-bye.